How do you accurately measure hundreds of volts in motor drives, EV powertrains, and charging stations while keeping the system safe, isolated, and rock-solid stable? You've got to step that voltage down safely, isolate the measurement path, and send a clean, drift-free signal to the control electronics. And this tech guide will break down exactly how the Vishay ISO-AC-VSAO Reference Design accomplishes this using the Vishay VIA0250DD, Vishay TNPV resistors, and the Vishay ACAS resistor network. If these capabilities matter for your design, this is a tech guide you won't want to miss.
Step 1. Safely scaling high AC voltages.
The first step in accurate high voltage measurement is safely scaling the input signal without sacrificing precision. So here's an engineer's challenge. How can up to 400 VRMS be measured without overstressing components or distorting the waveform? Well, the Vishay Reference Design handles this by using a properly rated high voltage divider built with precision Vishay TNPV resistors. This divider smoothly scales the voltage from UACIN to ref down to a safer, manageable UAC to ref level before it ever reaches the active circuitry. That helps keep everything protected and accurate right from the start. This resistor network maintains tight tolerance and low drift, helping to ensure the scaled signal remains accurate and linear, even under sustained high voltage stress. Proper voltage division not only protects downstream components, but also establishes the accuracy foundation for the entire signal chain. Interesting to note here, high voltage thin film resistors are engineered to minimize voltage coefficient effects, which helps maintain measurement linearity at elevated electric field strengths. By safely reducing the voltage first, the design prepares the signal for isolation and amplification in the next stage. So let's explore how the signal is isolated and amplified.
Step 2. Isolating and amplifying the signal.
Once the signal gets scaled down, the next challenge comes into play. How can the analog signal be transferred across a high voltage boundary while preserving accuracy and bandwidth? Well, the scaled signal feeds into the VIA0250DD isolation amplifier, which provides up to 1200 VRMS working isolation while maintaining a wide 300 kHz bandwidth for dynamic AC measurements. This amplifier reproduces the input signal across an isolation barrier and outputs a differential analog signal at out P and out N. The defined 1.44 volt common mode voltage helps ensure predictable downstream interfacing while maintaining reinforced electrical separation between high voltage and low voltage domains. Here's a fun fact. Isolation amplifiers not only enhance safety, they also eliminate ground loops that can introduce subtle but significant measurement errors in power electronics systems. With isolation established, the next step is making the differential output usable for modern data acquisition systems. We'll cover that next.
Step 3. Leveraging the differential output.
After isolation, the design presents another engineer's challenge. How can signal integrity be preserved in electrically noisy environments like motor drives or EV inverters? Well, we want to use the differential output directly. The VIA0250DD produces a balanced out P to out N signal centered at 1.44 volts common mode. That helps enable strong common mode noise rejection when paired with the differential ADC. Accessible pin headers make prototyping straightforward, allowing engineers to evaluate performance quickly or connect directly to precision data converters. Differential signaling helps ensure that external interference affects both lines equally, allowing downstream circuitry to cancel unwanted noise. An interesting note here is that many high-resolution ADCs achieve a better effective number of bits when driven by a differential input rather than a single-ended signal. While differential signaling is powerful, many systems still require single-ended inputs, so let's explore that next.
Step 4. Converting to a stable single-ended output.
In systems that use single-ended ADCs or measurement tools, we face an important engineering challenge. How is a differential signal converted to single-ended without gain drift or offset error? Well, the ISO-AC-VSAO design uses the AC-AS precision resistor network to perform differential to single-ended conversion. That produces a stable 0 volt to 2.5 volt output referenced to ground. Because the AC-AS network integrates tightly matched resistors with a single package, it maintains accurate resistance ratios across temperature variations. This minimizes drift and helps ensure the single-ended output remains proportional to the original high-voltage input. The resulting signal can be directly connected to microcontrollers, DAC systems, or multimeters. It's also important to know that in precision analog circuits, resistor ratio matching often has a greater impact on accuracy than absolute resistance tolerance. With the signal now ADC ready, long-term stability and dynamic performance become the next focus.
Step 5. Managing drift and bandwidth in real applications.
High-voltage systems rarely operate under static conditions, so here's another engineer's challenge. How can measurement accuracy be maintained across temperature swings and fast-changing AC waveforms? Combine low-drift components with a wide bandwidth isolation amplifier capable of tracking signals up to 300 kHz. The coordinated performance of the voltage divider, isolation amplifier, and resistor network ensures low offset and gain drift over temperature. This allows accurate tracking of dynamic waveforms in motor control loops, switching power supplies, and EV traction systems. Stability over time is just as important as initial calibration, especially in high-power applications. Did you know even minor temperature differences between discrete resistors in a divider network can introduce measurable gain shifts in precision sensing applications? With performance fundamentals established, thoughtful PCB layout and integration practices bring everything together. We'll cover that next.
Step 6. Integration best practices.
Following some practical tips will help ensure optimal performance in your design. First, validate your divider ratio against the full expected RMS input range before deployment. Maintain proper creepage and clearance distances to support up to 1200 VRMS isolation. Route high voltage traces separately from low voltage analog paths and keep differential traces symmetrical to preserve balance. You'll also want to place the AC-AS resistor network close to the amplifier output to minimize parasitic effects. And finally, make sure to test for system accuracy under both static and dynamic conditions. Careful integration protects both safety and precision.
Conclusion.
The Vishay ISO-AC-VSAO Reference Design delivers a complete solution for isolated high-voltage AC measurement. From TNPV scaling to VIA 0250DD isolation and AC-AS conditioning, every stage delivers accuracy, safety, and stability. To learn more about Vishay's comprehensive reference design, head over to mauser.com or click the link below, and be sure to check out our other tech guides because smart minds never stop learning.